Let's take a look at Singapore A-Level H2 Math 2022, Paper 1 together. So the first question that we are going to try solve is a complex number question. We are given two equations that involve complex numbers z and w. Let me write down the two equations first. The first one is I z plus 2w. This is equal to minus 1. And the second one is this 2 minus I z plus iw. This is equal to 6. We are going to try to solve them simultaneously to find z and w. So if you were to look at the two equations that we have here, I think one quick and efficient way for us to solve this simultaneously is to try to get this term and this term to be the same because they are already quite similar. What I need to do is to just multiply this equation by I, and if I were to multiply this equation by 2, then I'll get these two terms here to be the same as 2iw. So let's try that. So I'm going to multiply this equation by I. This will give me I times I, it will give me a negative z plus 2iw is equal to minus I. This I'm going to call it as equation number 1. This I'm going to multiply it throughout by 2. So we will have 2 times this is going to be 4 minus 2i. Then z plus 2 times this 2iw. That is our original plan to get 2iw in these two equations. This 6 multiplied by 2 gives me a 12. So this is equation number 2. So what I'm going to do next is to take equation number 2 minus away equation number 1. So it is going to be this minus this, which will give us a 4 minus 2i z. Then minus minus become plus z. 2iw minus 2iw, they will disappear. So we will be left with an right hand side as 12 minus minus I. It's going to be 12 plus I. Okay, now we have just z as the only unknown in our equations. Combine this together, we will have a 4 minus 2i plus 1. Z is equal to 12 plus I. So this will be 5 minus 2i z is equal to 12 plus I. So z is going to be equal to 12 plus I divided by 5 minus 2i. In order for us to write z according to what the question wants into the form of a plus ib, we are going to rationalize this. So I'll multiply the numerator and the denominator by the conjugate of the denominator, which is going to be 5 plus 2i. For the denominator, we will be getting a 5 square plus 2 square. For the numerator, 12 times 5, this is 60, then this times this, plus 24i, then this times this, 5i, this times this gives us a 2i square, which is going to be negative 2. So we will have a 58, 60 minus 2, 58. Then this plus this is going to be equal to 29i divided by 25 plus 4. This is going to be equal to 29. We will get this as a 2 plus I. Pretty nice number that we have gotten here. This is z. And I am going to just substitute z is equal to 2 plus I back into, I guess we can try back into this equation. Okay, let me call this equation number 3. Okay, a little bit weird. Okay, because this is the equation that is prior this equation number 1, but I guess it is still okay. Or else we can maybe change this to 1, then 2, then 3. Okay, but anyway, I am going to just sub this back into equation number 3. Okay, so we are going to substitute z, which we have found out to be 2 plus I, into this equation here, into equation number 3. So it is going to be equal to I z, which is going to be 2 plus I plus 2w. This is equal to minus 1. So we will have a 2i minus 1 plus 2w. This is equal to minus 1. This tells us that 2w is going to be equal to This bring over, oh, this will disappear. This is going to be equal to minus 2i. So this is an equal sign here, which means that w is going to be equal to just simply minus I. So z is equal to 2i, 2 plus I, and w is equal to negative I. Let's take a look at the next question. Question number 2. And question number 2, we are looking at a Maclaurin's question where part A require us to differentiate fx 2 times. So we are going to be getting f prime x and f prime prime x. And I think what I am going to try do, right, is instead of working with fx, okay, which I think it is still fine, it's just that what if we were to try to do a bit of change to fx is equal to tangent inverse square root of 2 plus y by letting y be equal to tangent inverse square root of 2 plus x instead, because by doing so I will be, it's just the notation, because by doing so I will be working with dy dx, d square y dx square, which I think personally for myself is easier for me to do a bit of implicit differentiation if everything is expressed in terms of y, f dy dx and d square y dx square instead of fx. So I'm going to try that by letting y be equal to fx, which means that y will be this tangent inverse square root of 2 plus x. And the reason is because I'm going to bring this tangent inverse over to the left-hand side to get this tangent y is equal to square root of 2 plus x in order for me to carry out implicit differentiation. Okay, I just don't like to have a fx is equal to this, then after if I have to bring tangent inverse over to the left-hand side, I will get a tangent fx is equal to, it's just not something that I'm that used to. So I'm going to use my notation to overcome that unfamiliarity. So I'm going to differentiate this equation here with respect to x. On the left-hand side, implicit differentiation, secant square y, then dy dx is equal to, on the right hand side, we're going to be just simply getting a 1. And secant square y is 1 over cosine square y, which means that dy dx here is going to be just cosine square of y, okay, multiplying the cosine square y over to the other side. This is going to be giving us a f prime x, because if y is equal to fx, that means this is going to be f prime x. But since f prime x is in terms of x, I think it is safer for us, especially when we are looking at an A-level question, right, to try to express f prime x in terms of x instead. To do that, I am going to make use of this. We can either try to go for trigonometric identities, or we can also draw a triangle to try to re-express this back into x. What do I mean by triangle? I think it is something that we have probably learned before, and it is extremely useful. So just in case you have forgotten about it, do try to check it out, or just maybe you can even learn it directly from here again, or to recall it directly from here, okay? So I'm going to make use of this, and I'm going to just draw a right-angled triangle. Yeah, the triangle that I meant was a right-angled triangle. So tangent y, if I were to see y as the angle, will be opposite over the adjacent. So it's going to be square root of 2 plus x. Opposite over the adjacent is like divided by 1. So here is going to be 1. Applying the Pythagoras theorem, here is going to be square root of 1 square plus this square. So here will be square root of 1 plus square root of 2 plus x squared. And based on this, I can actually come out with cosine y. Cosine y will be this divided by this, correct? So cosine y will be 1 over square root of 1 plus square root of 2 plus x squared. And we are looking at cosine y squared. So this is going to be giving us a 1 over 1 plus square root of 2 plus x squared, and this is f prime x. And we are supposed to also get an expression for f prime prime x. So we need a d square y dx squared. And in order for me to do that, instead of trying to do a differentiation for this, which I think it is actually not too bad, okay, but I feel that it is actually going to be even easier if I were to just do a bit of implicit differentiation using this. So I'm going to try making use of this instead, but by all means, okay, go and try differentiating it directly from here. I think it is still going to be pretty okay. So I'm going to differentiate this to get a d squared y dx squared, which is going to be f prime prime x. So differentiating this with respect to x, we are going to be doing an implicit differentiation. It is going to be 2, then cosine y minus sine y, then dy dx, which will be minus 2 sine y cosine y dy dx. And now let us try to re-express this back into x by making use of our triangle again. So minus 2 sine y, opposite over the hypotenuse. So this is going to be equal to square root of 2 plus x over the hypotenuse, which is square root of 1 plus square root of 2 plus x squared. Then cosine y. Cosine y will be, okay, will be what we talked about just now. It is going to be 1 over square root of 1 plus square root of 2 plus x squared. And then dy dx. dy dx, we have it here, right? This is our dy dx in terms of x. So it's going to be 1 over 1 plus square root of 2 plus x square. Okay, pretty simple. If you were to ask me, like this here, if I were to just multiply it out, okay, I'll be getting a negative 2 of this. In the numerator, is just that. So negative 2 of square root of 2 plus x, then divided by this times this, it is actually the same thing. Okay, so it's as if this is going to be squared, which I'm going to be getting this. Okay, so it's going to be this multiplied by, this times this multiplied by this will be getting us this 1 plus square root of 2 plus x square and the whole thing square. So this will be f prime prime x. Let's move on to B, and please allow me to just clean what I have on the board. It's really getting a little bit crowded here. So this is f prime prime x, this is f prime x. Let me just rewrite it here first, okay? So we have our fx to be this, fx to be equal to this, and f prime x is this. So it's going to be 1 over 1 plus square root of 2 plus x squared. So fx is this, and f prime prime x, we've just found out. F prime prime x is equal to negative 2 square root of 2 plus x. Then divided by, we have a 1 plus square root of 2 plus x square. Okay, let me erase the rest of the information that I will not be needing. So let me erase. So for B, we are supposed to find out the Maclaurin's series of fx, and we are going for the first 3 terms of this Maclaurin's, which means that we will go all the way for differentiation wise. Okay, we'll go all the way up to f prime prime x, which we have. So it is from this expression here. And let's not forget about the fact that the question requires us to give the coefficients to 3 significant figures. So for part B, we will first need to find out what is f0. Okay, if we were to make use of the Maclaurin's series definition from my formula sheet. So we will need f0. So f0 is going to be tangent inverse square root of 2 plus 0. So I'm going to just leave it as it is here. And we will need f prime 0, which is going to be 1 over 1 plus square root of 2 plus 0 square. So this is going to lead me to a 1 over 1 plus 2, 3. And we will need f prime prime 0, which is minus 2 square root of 2 plus 0 over 1 plus square root of 2 square. So this is minus 2 square root of 2 over 9. Yep. Okay, over 9. So with this, we can now find the Maclaurin's series for fx. It is going to be equal to f0 plus f prime 0x, then plus f prime prime 0 divided by 2 factorial x squared and so on. So it is going to be equal to tangent inverse square root of 2 plus 1 over 3x. Then we will have a minus 2 square root of 2 over 9 divided by 2 factorial of x squared all the way until infinity. We will press it into the calculator so that we can get the coefficients to be in 3 significant figures. So pressing this into the calculator, giving to 3 significant figures is 0.955. Plus this is going to be 0.333x. And then this will be negative 0.157x squared. And all the way up to infinity. Let's move on. Let's take a look at question number 3. So for question number 3, we are given a pair of parametric equations that represent a curve. Let me write down the 2 parametric equations first, okay? So we have this x is equal to 1 over 2 e to the power of 3t plus 2e to the power of negative 3t. And we have y as 1 over 2 e to the power of 3t minus 2e to the power of negative 3t. In part A, we have to find the gradient of the normal to the curve at a point when t is equal to 1 over 3 ln 2. So what we will need is dy dx. Okay, because from dy dx, we will be able to deduce the gradient of the tangent when t is equal to 1 over 3 ln 2. Then from the gradient of the tangent, we will deduce the gradient of the normal that the question wants. So to find dy dx, let's first work on dx dt. This is going to be half. Differentiating this with respect to t, it is going to be 3e to the power of 3t. Differentiating this with respect to t, it will be 2 multiplied by negative 3, which is going to be from chain rule. Then means we will be having a negative 6e to the power of negative 3t. And for this, let us find dy dt. It is going to be half, then 3e to the power of 3t. Then negative 2 multiplied by negative 3 gives me positive 6e to the power of negative 3t. And from here, we will be able to find dy dx. And dy dx is dy dt over dx dt. So it is going to be half, then 3e to the power of 3t minus 6e to the power of negative t divided by, I should be writing this first, dy dt. So it is a plus here, half 3e to the power of 3t plus 6e to the power of negative 3t divided by dx dt. Then it is this. So it's going to be then half 3e to the power of 3t minus 6e to the power of negative 3t. In fact, we can also, other than crossing this away, okay, we can also divide the numerator and the denominator by 3 at the same time, which will then leave us with e to the power of 3t plus 2e to the power of negative 3t divided by e to the power of 3t minus 2e to the power of negative 3t. I'm going to leave it as it is at this, in terms of this expression here. I don't think I will try to simplify any further because I just want the numerical value of dy dx when, let me write it down here, when t is equal to 1 over 3 ln 2. So when t is equal to negative 3, when t is equal to 1 over 3 ln 2. So when t is equal to 1 over 3 ln 2, let's find out what is the gradient of the tangent at this point. So that will be e to the power of 3, 1 over 3 ln 2, replacing t here by 1 over 3 ln 2, then plus 2e to the power of negative 3, 1 over 3 ln 2 over, this will be e to the power of 3, 1 over 3 ln 2 minus 2e to the power of negative 3, 1 over 3 ln 2. Okay, dy dx is going to be equal to this. We can definitely and we should definitely simplify this. So 3 and 3 can be cancelled. We will have e to the power of ln 2, which is going to be just 2. And this 2, of course, I'm going to just leave it there, okay? But for this, 3 and 3 can be cancelled. We're going to be left with a negative ln 2, which I am actually going to be, let me rewrite here. I'm going to rewrite this e to the power of negative ln 2, okay? The e to the power of negative ln 2. I'm going to rewrite this as e to the power of ln 2 to the power of minus 1, which is going to be e to the power of ln half. Okay, because if I can just work on it in this form, that means what I'm going to be left with for this, which is this, is just going to be equal to half. Okay, it's like way simpler, definitely. I'm going to try that for the denominator also. 3 and 3 can be cancelled. This is going to be 2 minus 2, just like what we have discussed here. This is going to become a half. So we will have a 2 plus 1 over 2 minus 1. This is going to give us a 3, which means that the gradient of the normal will be negative 1 over 3. This is part A. Let us check out part B. Part B, the question actually is giving us a bit of help. By considering x squared and y squared or otherwise, we are supposed to find the Cartesian equation of the curve. So the Cartesian equation will be involving definitely x and y, but excluding t. So the hint, we are going to try to make use of it. We are supposed to look at x squared and y squared, okay? So what is x squared? X squared is going to be equal to half square is 1/4. So we have a e 3t plus 2 e to the power of negative 3t squared. And y squared will be 1 over 4 e to the power of 3t minus 2 e to the power of negative 3t squared. Okay, these two expressions that I've gotten here doesn't seem to be too easy for us to be combining them together in such a way that t will disappear. But I can see the similarity definitely. So one way that we can try to maybe manipulate this a little bit to get us more perspective of the expression of x squared and why they are probably going to be pretty useful in terms of getting the Cartesian equation is maybe I'm going to just try to expand this, okay, to just get another perspective of how this can be observed. So if I were to expand this, it is like a plus b squared. It will be a squared plus 2ab plus b squared. So it will be this square e to the power of 6t, then plus 2 times of this times this, which will be, it's just going to be 4. Okay, because 2 times of this times this, 2 times 2 is going to be 4, but this times this is going to be e to the power of 3t times e to the power of negative 3t will be e to the power of 0, which is going to be equal to 1. So it will be 4 times 1. Then plus this square, which will be 4e to the power of negative 6t. As for this, if I were to expand, a minus b squared will be a squared, which is going to be e to the power of 6t, minus 2 times of this times this, minus 2 times of, it will be minus 2 times 2, it will be minus 4. Then e to the power of 3t multiplied by e to the power of negative 3t gives us e to the power of 0. Similarly, it is going to be equal to 1. So it's going to be negative 4 times 1 plus this square, which will be 4e to the power of minus 6t. And now we see something that we can really work on, because these two terms are exactly the same. This is 4 minus 4. So what if we were to just take this as, let's say, equation number 1, this as equation number 2, we can do equation number 1 minus equation number 2. Because by doing so, on the left-hand side, we will have x squared minus y squared. And on the right-hand side, basically, it will be 1/4 of this minus this, it will disappear. This minus this is going to become 4 plus 4. This minus this, it will disappear. So now we are going to be left with x squared minus y squared is equal to 1/4 times 8 is going to be equal to 2. Nice. This is our Cartesian equation. And we are supposed to be trying to state any restrictions that is on the values of x, which is this x over here. And to me, when I want to try to discuss about restrictions on the values of x, when I want to try to discuss about many different values of x, which is what the question is hinting to us, okay? The question says the values of x. I don't think I will try to work on this too algebraically, because something that is a bit more algebraic, I find it more useful when if I were to try to work on observation of the expression, right? It is more useful if I were to do substitution to find 1 or 2 values of x or y. But when I need so many values, okay, I'm expecting restrictions. That means I'm expecting a range of values of x. I don't think looking at the expression by itself, observing from expressions, right, are usually that helpful. But one other perspective, I think it is way more useful, which is to try to look at this from the graphical point of view. Because graphs gives us the possibility of not just looking at single values of x, it gives us the possibility of looking at a set of values of x. Because of the way that the graph is drawn, I will be able to observe many different values of x that is on that graph at the same time. So with this in mind, with this as my strategy to try to work on the very last part, I'm going to just do a quick sketch of this, which is actually very simple. Why? Because this is one of the standard graphs that we have memorized in our syllabus. This is a hyperbola. So let me just do a quick sketch of this hyperbola. I don't think the sketch is going to get us much marks. So let's skip the details of the hyperbola and draw what that is essential. Okay, that means what is going to tell us something about the range of values for x. So for this hyperbola, it is going to be one that will have a center at the origin. So the two asymptotes will be passing through the origin. Okay, so this is O. And the shape of the hyperbola is going to be like this, right? So it will be like this and like this. Okay, it is not necessary. Probably you guys will be able to do that algebraic observation about how the feature is going to be, the feature of the algebra is going to be like for an equation that is like this. But just let me do a quick manipulation to this so that the feature will be maybe even more prominent to us, which is, I'm going to bring this to the denominator, okay? So it is going to be this. Then y squared over square root of 2 square is equal to 1, which means that the horizontal radius of this hyperbola, the horizontal radius is going to be square root of 2. So 0 plus square root of 2, this is going to be square root of 2. 0 minus square root of 2, this is going to be when x is negative square root of 2. And this is going to give us the insight to the restrictions on the possible values of x. Because if I were to look at this and then looking at the graph, this graph tells me where x is going to be existing, where are the values of x. Okay, so looking at this graph, I know that x is supposed to be less than or equal to negative square root of 2, or x is supposed to be bigger or equal to square root of 2. And this forms for us that restriction that the question is saying. But there's still one more twist to this question, which is this graph didn't originated from this equation alone. This equation can be traced all the way back to this pair of parametric equation. So we do need to consider the original equation that was given to us by the question, which is actually this version of x. And if you to look at this version of x with a e to the power of something plus 2e to the power of something, I mean e to the power of anything, okay, as long as that anything, that power is a real number, okay, because we have learned complex numbers, so we know you know, if it's complex number, things may change a little bit, but we are definitely not working with complex number for our parametric equation. So if I have e to the power of something plus e to the power of something, which means that this expression here is going to be positive all the time. So since we are talking about x being half e to the power of 3t plus 2e to the power of negative 3t, this will be positive for all values of t. So since this is always going to be positive, we have to be rejecting this. That is why my final restricted set of values for x that will answer for me this question will be when x is bigger or equal to square root of 2. So this is question number 3. Let's take a look at the next one. Yep, question number 4. In question number 4, A, we are supposed to do a differentiation to show that differentiating cotangent x is equal to that. So let's try differentiating cotangent x, which is the same as differentiating tangent x, 1 over tangent x, which is tangent x to the power of minus 1. So differentiating this is going to be minus tangent x to the power of minus 2, then differentiating tangent x, this gives me a secant square x. So this is going to be a minus, here we will have a 1 over tangent square x, and then a secant square x, okay? And I think we should try to re-express this into sine and cosine in order for us to try to simplify it further. Hopefully we will be able to, and we will be able to prove that it is equal to negative cosecant square x, which is negative 1 over sine square x. So negative, I'm going to just leave it. So 1 over tangent square x is sine square x over cosine square x. Flipping it, it is going to be cosine square x over sine square x. Then secant is 1 over cosine, so secant square is 1 over cosine square. So this and this can be cancelled. I will be left with a 1 over sine square x, which is negative cosecant square x. Okay, this is what the question wants us to show. And in part B, we are going to do a trigonometric identities. Okay, it is just like what we have done in our secondary school. I'm going to start with the left-hand side, which is giving me a sine 2x tangent x. And sine 2x, we are going to change it into just x, okay? So sine 2x, change it into just a single angle. This is double angle. It is going to be 2 sine x cosine x tangent. Let me just re-express it as sine x over cosine x. So cosine x can be cancelled. I'm going to be left with 2 sine square x, which is what the question wants me to show on the right hand side. Maybe I should just say that this is equal to the right hand side. Okay, a slightly more familiar presentation as my secondary school. C, we are supposed to make use of what we have now to do some integration. Maybe let me just erase the board a little bit, okay, and leave myself with the kind of information that I need, which is this here. This here is giving me a negative cosecant x. Okay, this is from 4a. And for 4b is basically just recopying the question. Oh wait, this is also just recopying the question. So anyway, for 4b, we have a sine 2x tangent x. This is 2 sine square x. Okay, we are going to try and make use of probably both a and b. We are not sure yet at this moment, but the question says hence, so we will definitely need to make use of the previous parts. So for C, we are supposed to find the integration from pi over 18 all the way until pi over 9 of cosecant 6x, then cotangent 3x. Okay, let's see how we are able to at least relate this or whatever that is going to be coming up to A and B, okay? I think what I'm going to try do is to try to change what I have here into, okay, actually I should change this. I'm going to change this cosecant 6x to 1 over sine 6x. And cotangent, I will change it to 1 over tangent. I have a reason for this. Let me just show you what I have first as an expression, then let me explain to you what I've seen, okay? So this is going to become a 1 over sine 6x, and this will become a tangent 3x. Okay, and the reason why I'm changing into this is because from B, I can apply the identity that I've just proven. How do I do that? Let me just rewrite this further. Here is pi over 9. So this, I will write it as sine 2 times of 3x. And then tangent, I will continue to write it as 3x. So based on the identity that we have here, right, it's like replacing x by 3x, replacing x by 3x, which means that what I am going to be left with in the denominator after I apply the same identity as part B is I'm going to be left with a 2 then sine square. Since x is replaced by 3x, so I'm going to be left with this, which I can also rewrite this as integration from pi over 18 all the way until pi over 9. I can also rewrite this as 1 over 2 of cosecant square 3x dx, right? 1 over sine square 3x is cosecant square 3x. And the reason why I also have motivation to write this is because of what I've gotten here. I'm going to take out not half but negative half, so I can generate a negative here, which will be a negative half integration from pi over 18 to pi over 9 and a negative cosecant square 3x dx. So how are we able to make use of the result that we have obtained from part A to try to do an integration for this? Because from what we have in part A over here, we differentiate this, we are getting this, which means that when we are integrating the right hand side, negative cosecant square x, we will be getting a cotangent x plus c. And this can give us another version of what we have learned in our syllabus for the fx, f prime x kind of integration, because we can just rewrite this. Let me rewrite this into the fx, f prime x format, okay? So if I were to replace x here by fx, to make it work, we will just need a f prime x here, then negative cosecant square, then replacing x by fx. So this will be cotangent fx plus c. Okay, this is how I'm going to be making use of part A to try to integrate this. Because now if I were to make use of this, which is derived from here then to here, what I'm going to do is I am going to try to see fx as 3x, which means that f prime x is going to be just simply 3. I need a 3 here in order for it to become something similar to this. So I'm going to divide by a 3 outside. So 1 over 2 dividing by a 3 outside, or multiplied by 1/3. Then it will be integration from pi over 18 all the way until pi over 9 of 3. Then here we will have a negative cosecant square. This is my fx dx. And according to this is negative 1 over 6. And according to what we have just discussed here, what we are going to be getting out from my integral will be this, which is going to be cotangent of fx. Fx is 3x. So cotangent of 3x then from pi over 18 all the way until pi over 9. Now we can substitute the upper and lower limit into this to evaluate my integral, giving it in the exact value according to what the question wants. So it is going to be negative 1 over 6. And substituting this in, we are going to be getting a cotangent pi over 3. Minus away, substituting this in, it is going to be a cotangent of pi over 318. This is going to be pi over 6. So special angles are what we are working on. So cotangent of pi over 3 is going to be 1 over square root of 3. Then this is going to be square root of 3. I think this is fine, or we can also multiply the negative inside to make it a little bit nicer looking, maybe. So multiplying the negative into here will be square root of 3. Multiplying negative into here will be minus 1 over square root of 3. And this is question number 4. Let's move on and take a look at question number 5. Before I move on, I just want to highlight a correction that I need to make for here, because I'm not sure why, but this appeared as 3. So, okay, that was actually the gradient of the tangent, but just now, according to what we have calculated, we are supposed to be finding the gradient of the normal. So if the gradient of the tangent is 3, then the gradient of the normal should be negative 1 over 3. Okay, so I've corrected here as the answer for question number 3. So anyway, let's move on to question number 5 over here. For question number 5, we have a line y is equal to mx. This is a linear line and it is tangent to the curve that is given to us. In fact, this curve is a circle. So we are supposed to show that m satisfies that equation over there. The first thing that I'm going to try do for this question number 5, part A, is to try to solve this y is equal to mx and the equation of the curve or the circle as a pair of simultaneous equation. Okay, because according to the question, this line and the curve, they are going to be tangential to each other, which means that if I were to be solving simultaneous equation, I will be expecting one single solution, because there will be just one single intersection. So solving simultaneous equation, y is equal to mx. Let me call this equation number 1. And for the curve, which is a circle, we have a x plus 8 square plus y minus 14 square. This is equal to 52. I am calling this equation number 2. I will just sub equation number 1 into equation number 2. So replacing all the y by mx, we will have a x plus 8 square plus y, which I'm going to replace it by mx minus 14 square. This is equal to 52. Let me expand this. So we will have x square plus 16x plus 64. This is going to be m square x square minus 28 mx plus 14 square, which is 196. This is equal to 52. I will bring everything over to the left-hand side, and I'll group all the coefficients of x square, x, and the term that are independent of x together. And that will leave me with an m square plus 1 x square. And the next term is going to be equal to 16 minus 28 mx. Then we will have a 208. This is equal to 0. Like what we have thought the solution is going to be in the very beginning, because the question says that this and this, they are tangent to each other. This equation here, we will be expecting just one single solution. And it is a quadratic equation. For a quadratic equation to have just one single solution, that will be when the discriminant is equal to 0. So I'm going to let the discriminant be equal to 0, which means that we are talking about b squared minus 4ac 208. This is equal to 0. Expanding this, we will be getting a 256 minus 896m plus 784m square minus 832m square minus 832. This is equal to 0. And simplifying this, we will be getting a negative 16 3m square plus 56m plus 36. This is equal to 0, and removing the negative 16 dividing over to the other side, this will leave me with a 3m square plus 56m plus 36 is equal to 0. And this is actually the equation that m should satisfy that the question wants me to show. So this will help me to finish question number 5, part A. And the question went on to say that points A and B are on this curve where the tangent at point A and the tangent at point B intersect at the origin. In fact, what we are looking at is a scenario where we have a tangent, okay, which is going to be, the equation of this tangent is already telling me that this tangent is going to be intersecting the origin. So it is actually this tangent that is going to be, that is mentioned in this second part of the question where we have these points A and B. Let me just do a quick sketch of the diagram based on this. And of course, we're going to be making use of this to solve for M so that we have a better idea of how the scenario is like before we continue with part B, okay? Let me erase this first. And we have this, which is, let me write it down here, 3m squared plus 56m plus 36 is equal to 0. So if there were to be these 2 points A and B where the tangents are going to be intersecting the origin, so this is a circle with the center at -8 and 14. The radius is going to be square root of 52. I have pressed it into the calculator. Square root of 52 is 7.2 something. So, which makes this circle that we are talking about, right, to be hovering in the second quadrant, maybe something that is like this. Okay, y and x. So the center is at -8 and 14. And if I were to be sketching a tangent such that, and we know that this tangent is going to be passing through the origin, okay? So if we were to be sketching this linear line such that it is a tangent to this curve, it is going to be either here, so it will pass through the origin, or it will be somewhere here, okay? And it's supposed to intersect at the origin. So that is why, according to what the question says, there will be this point A and point B, or I can also swap this. I don't think it really matters. So if it is a scenario that is like this, then what we can try do is to find the equation of this tangent. Okay, then we will be able to try find the coordinates of this point. So for part B, in order for us to find the equation of this tangent, and of course, we're also going to try to find the equation of this tangent, okay? We're going to solve the equation that we have previously, which is this 3m squared plus 56m plus 36, which we have shown from the previous part. So from my graphing calculator, pressing into my calculator, I'm going to get m to be equal to -2/3, or m to be equal to -18. And from the previous part, when we were trying to solve this as a pair of simultaneous equation, we actually derive at this particular equation. Let me just rewrite it down here, okay? We derive at this m squared plus 1x squared plus 16 minus 28m x plus 208. This is equal to 0. So this was the equation that was the result of me trying to solve for this and this. And now when m is equal to -2/3, let me just try, okay? So when m is -2/3, substituting into this equation, we will have a negative 2 over 3 square plus 1 x square plus 16 minus 28 multiplied by negative 2 over 3, then x plus 208. This is equal to 0. And we will be getting a 13 over 9x squared plus 104 over 3x plus 208. This is equal to 0. And then making use of my calculator, solving for this equation, we are going to be getting x to be equal to negative 12, which is in a way expected, isn't it? Because we are expecting this equation, which was derived, which was, sorry, we're not expecting this equation. We are expecting this equation, with this being the m that is substituted back into this equation, to be giving us just one solution. So one solution for x, which is what we are seeing right here. This is giving us just one solution for x, and substituting this back into this equation here, which is, so when x is equal to this, y will be equal to mx, and m is this. So minus 2 over 3 multiplied by x. So y is going to be equal to 8 over here. So we are talking about, for example, like this line here to be y is equal to m, which is minus 2 over 3x. So we're getting this. So this tells me that the coordinates of one of the points, which is mentioned by the question, let's say that point is A, is negative 12 and 8. We're going to repeat the same process, okay, for this other line over here. That will be when I make use of m to be equal to negative 18. So y is equal to negative 18x. Let me continue here. So when m is equal to negative 18, once again, substituting this back into this equation that we have derived previously by trying to solve this as a pair of simultaneous equation, it is going to be equal to negative 18 square plus 1x square plus 16 minus 28 multiplied by negative 18 x plus 208. This is equal to 0. So simplifying this will be getting me a 325x squared plus 520x plus 208. This is equal to 0. Pressing into my calculator, solving for this, how many solutions am I going to be expecting? I'm going to be expecting one solution, because this is the m that I'm using, which will be giving me one single solution for this quadratic equation. So pressing into my calculator, true enough, x is equal to negative 4 over 5, which means that y is, I'm substituting this into here, okay? Y is going to be equal to negative 18 multiplied by negative 4 over 5. This is equal to 72 over 5. This gives me the coordinates of this point here. So therefore, for point B, it is negative 4 over 5 and 72 over 5. This is for question number 5. Let's take a look at question number 6 together. It is a question that is going to be involving sequence of transformation, so graphical transformation, and also in part B, C, and D, it is actually changed into a functions question. So we are starting off with a function that is given to us in question number 6a over here as fx to be equal to ax plus k over x minus a. And the question requires us to describe fully a sequence of transformations, which is going to be transforming the curve from y is equal to 1 over fx to this. Y is equal to 1 over fx to this. So if you think about it, to go directly from y is equal to 1 over fx to an expression that is like this, and if I were to make use of the transformations that I have learned according to what I'm taught in the school, I don't think it is actually that easy for me to observe the kind of transformation that is going to be, the kinds of the kind of transformations that are going to be taking place. So what we need to do is to do a bit of manipulations to this first, so that at least, okay, what we have been taught in our school can be applied to describe that series of transformation. What I mean is, if you were to just try to do a bit of manipulation to this, for example, right, let me show you, okay, if I were to either do a long division to this, or if I were to, let's say, just try to do a bit of algebraic manipulation by doing something that is like this. Okay, I'll take x that is here, I minus a plus a, so that I can have a term that is like this, then multiply to a. So if I can then regroup it further, I will have this plus a squared plus k over x minus a, where I take this divided by this is going to give me an a. Then this over this is like an a squared plus k over x minus a. But let's not forget about a and k, which are constants, which means that I can also try to view this as a plus a constant, a squared plus k, multiplied by 1 over x minus a. And this form, okay, this red color form, is the one that is easier for us to, through observation, associate it back to the expression of 1 over x, which I can then describe a sequence of transformation that is in accordance to what we have learned in our school. So if I were to start with 1 over x, what I can try to do is, for this 1 over x, I'm going to replace x by x minus a. So then I'll be getting a 1 over x minus a. Then I'm going to multiply this by this constant here. So it will be a squared plus k multiplied to this 1 over x minus a, which will be giving us an a squared plus k over x minus a. Then I will add the whole thing to a. So it will be then a plus a squared plus k over x minus a. And this series of replacement, multiplication, and addition is the one that is going to be giving me a sequence of transformation that is in accordance to what we have been taught in our school. Because from here to here, we replace x by x minus a. So the first transformation is going to be a translation, right? It is going to be a translation by a units in replacing x by x minus a. So we are translating by a units in the positive x direction. Then number 2, we are going to be multiplying this by a squared plus k. So multiplying this by a constant, it is going to be a scaling by a factor of this constant parallel to the y-axis. So I'll just do that here, scale by a factor of a squared plus k. Okay, we need to be able to see this as a constant in order for us to describe what is scaling. So by a factor of a squared plus k parallel to the y-axis. Then we are adding the entire expression here by a. So the last transformation, okay, adding this entire expression by a constant is going to be causing the graph to be translated vertically. And if you are adding it by a, then it is going to be a translate by a units in the positive y direction. Okay, this will be the sequence of transformation, which means that we are supposed to do this first, then this, then this. This is for part A. Let's take a look at part B. For part B, we are supposed to find f inverse x. So for B, we are going to let y be equal to fx, which means that y will be ax plus k over x minus a, where we are also given that for fx, x cannot be equal to a. Pretty obvious, I guess. When x is equal to a, the denominator of the expression will become 0. So yeah, it is going to become undefined. So x definitely cannot be equal to a. Let's try to manipulate this and make x the subject. Cross multiplying, we have xy minus ay is equal to ax plus k. And I'm going to move all the x over to one side. So I'm going to leave this here. Then minus ax is equal to this. If I were to move it over to the right hand side, we have ay plus k, which means that we have a x of y minus a is equal to ay plus k. So x is ay plus k over y minus a. And this is going to be the one that is giving us the expression for f inverse, right? So f inverse x is going to be equal to, using this expression here, replacing all the y by x, it will be ax plus k over x minus a. And are we able to see something that is special about this f inverse? Because in order for us to do part C, we need to see this something special that is ongoing for this, okay? Can you see that this expression here is actually exactly the same as the expression for fx? Okay, and that is why if I were to make use of this, then I can hence, in part C, hence or otherwise find f2x. So for f2x, this is the same as ffx. And since f is the same as f inverse expression, I can also write this as f inverse x. So this is going to be equal to just simply x. This is for part C. Then for part D, we are going to still make use of this as what we are going to be, we are still going to make use of this to hence find something that is like this, f2023 of 1 in terms of a and k. How are we going to make use of the result from C to try to deduce for this? Let's first make sure that we understand the notation. The notation is f20231, which means that we are looking at something that is like this. We are looking at this to be like a composite function, just like what we are doing here. Okay, f2x is ffx, which means that we are talking about this, where we are going to be doing composite functions, like many composite functions of 1. In fact, we are looking at 2023 functions f being composite together. And from part C, we know that if two composite functions of f are like carried out, two functions of f are composite together, I'm going to be getting back this x. Okay, f2x, I'm going to be getting back this, the input x, which means that this that is here, f2x, f21, I am going to be getting this back as 1, which will then leave me with this, all the way until this, 1. So I'm going to be left with now from 2023, this is going to be something that is like 2021 of 1, because two of the functions has sort of like collapsed. Okay, or it has been, I mean, ff1 is going to be returning just 1. So we are like moving, we are reducing by two functions f. And if I were to just continue with the same way of like removing the two f's based on part C, this will become 1. So I'm going to be left with this, and it will be this 1, because this will be collapsed to this, which means that now this is going to be like f2019 of 1. So if this trend were to just keep on going and continuing, we are looking at this to be like, f of the ones that are going to be collapsing will be like even numbers of composite, right? So it will be like f, then the other one that I'm going to be looking at will be all the rest of the even numbered times of composite, which is going to be 2022 of 1, which will collapse to just 1. That means f20221 will become just 1. So what is f1? I just need to replace all x by 1. So it's going to be a times of 1 plus k over 1 minus a. My final answer here is going to be a plus k over 1 minus a. This is for question number 6. Let's move on to question number 7. Let's now take a look at question number 7. And we are given the equation of curve C as y is equal to x to the power of negative 3 ln x. In part A, we are supposed to try find dy dx. So it is easy and straightforward. This is just going to be applying the product rule. I'm going to hold this expression here constant. I'll differentiate this, which will give me a 1 over x, plus differentiating this expression, it is negative 3x to the power of negative 4, then ln x. We will have a 1 over x to the power of 4 minus 3 ln x over x to the power of 4. Combining this into one single expression, we have a 1 minus 3 ln x over x to the power of 4. And this is what the question requires us to show. And hence, we are supposed to find the coordinates of the turning point of C. And at turning point, dy dx is equal to 0. So let's make dy dx here to be equal to 0. So we are going to be letting 1 minus 3 ln x over x to the power of 4 to be equal to 0. Multiplying x to the power of 4 across to the other side, this is going to be equal to 0, which means that ln x is going to be equal to 1 over 3. X is going to be equal to e to the power of 1 over 3. We are supposed to find the coordinates of the turning point. So we need the y coordinates also. So from here, we are going to find the corresponding y coordinates by substituting this back into this. So we will have e to the power of 1 over 3 to the power of negative 3 ln x, which is going to be e to the power of 1 over 3. So this, we are going to be getting e to the power of negative 1. And this is going to be 1 over 3. So this will be 1 over 3e. So the coordinates of the turning point is going to be this e to the power of 1 over 3. And the y coordinates will be 1 over 3e. Let's go to B. So in part B, we are going to be working on finding the exact area that is going to be bounded by this curve C, the x-axis, and the line x is equal to 3, which is a vertical line. And I think the very first thing that we should try to do when we see a question that is like this is to make use of our graphing calculator to sketch a graph so that we can visually identify the region that the question is talking about. So based on my graphing calculator, let me just do a quick sketch of the graph that I am going to be expecting. This is the y-axis, this is the x-axis. I will be expecting a graph that is something like this, where here is going to be 1 and x is equal to 3 is going to be reference to here, this x coordinate here. So the region that the question is asking for, the region that is going to be bounded by this curve C, the x-axis, and the vertical line x is equal to 3 will be this region here. And to find the area of this region, we are definitely going to be making use of integration. So it will be integrating from 1 all the way until 3 of the expression of curve C, which is x to the power of negative 3 ln x. We could have pressed our calculator if it is not because of the fact that the question is asking us for the exact area. So we need to do this integration manually. What we're going to try to do is integration by parts, making use of the acronym that we have mentioned in our theory outline on the Achevas TV. We are going to be assigning this, which is algebraic, as A, and this, which is logarithmic function. So I'm going to assign L to it using LIATE to help me to make the decision. I'm going to make U to be L because L comes before A in LIATE. So I will be letting U be equal to ln x and dv dx let's make it this x to the power of negative 3. So based on this, we can then find du dx, which is 1 over x, and v is going to be x to the power of negative 2 over negative 2, which is negative 1 over 2x squared. So now this can be re-expressed using integration by parts formula. It is going to be uv. So here is going to be u, which is ln x, multiplied by v, which is negative 1 over 2x squared. And let's not forget about the lower and upper limit, 1 to 3. Then minus integration from 1 to 3 of v du dx. So it is going to be equal to this multiplied by this. So it will be minus 1 over 2x squared multiplied by 1 over x. This, we can just very easily substitute the values in. Okay, so if I were to substitute 3 in, we are going to be getting a negative 1 over 18 ln 3. Then minus substituting 1 in, ln 1 is 0. So it is actually going to be 0 for the second expression. Then minus away integration of this. Okay, let's bring this negative half out. So it will become negative, negative, it will be plus 1 over 2 integration from 1 to 3 of 1 over x to the power of 3. So 1 over x to the power of 3, I think let's just rewrite it as x to the power of negative 3. I think it is definitely going to be easier for us to carry out the integration process, because we are looking at the x to the power of n over here. So this that we have here is negative 1 over 18 ln 3. I'm going to leave it as it is, plus 1 over 2 integrating this x to the power of negative 3 plus 1, so x to the power of negative 2 over negative 2 from 1 to 3. This is minus 1 over 18 ln 3. Let's bring out negative 2 from the denominator, which will give us minus 1 over 4. So we are going to be having a x to the power of negative 2 or 1 over x squared from 1 to 3. This is minus 1 over 18 ln 3 minus away 1 quarter of 1 over 9 minus 1. So my final answer that represents the exact area of this region is going to be equal to, here we are going to have a 2 over 9, then minus 1 over 18 ln 3. So this is question number 7. Let's move on to question number 8. Okay, let's check out question number 8 over here. It is another integration question. So in question number 8, we are first supposed to integrate 2x minus 1 over x squared plus 2x plus 1. In order for me to integrate this, I am going to try letting the denominator be fx, which is x squared plus 2x plus 1. And if I were to try f prime x, it is 2x plus 2. And I think it is potentially possible for us to have this 2x plus 2 as an expression that will appear in the numerator. Because there's a x here, so, and with a 2, which synchronized to this, let's just go for a 2x. Then we need a plus 2, so I'll plus 2 and I'll minus 2, and then there's this original minus 1 here, and my intention is to have this as one expression by itself. So this divided by x squared plus 2x plus 1, which I can then break this up into two different expressions. One will be this over this, so it is going to be this 2x plus 2 over x squared plus 2x plus 1. And this is a good expression for us to be working on as an integration question, because this is fx and now this is f prime x. And as for the other expression, we have a negative 3. This negative 3, let us just bring it out of the integration notation. So it is negative 3, then I'll have a 1 over this expression over here. By itself, I think it is harder to see how it can be integrated. So let's do a quick manipulation to it by, let's say, doing a factorization. Factorizing the denominator actually gives us just x plus 1 squared, which is perfect because bring this to the numerator with a x plus 1 to the power of minus 2, it is very, very easy for us to integrate. Let me just rewrite this so that it's easier for us to follow through. So this is going to be my f(x) is, sorry, my f prime x is this, and f(x) is this x squared plus 2x plus 1. And for this, let me just rewrite this as this, which is easier, at least for me, to carry out the process of integration. So this will be ln of x squared plus 2x plus 1. And in fact, we know that x squared plus 2x plus 1 can be factorized into x plus 1 squared, which is going to be bigger or equal to 0 all the time. So it is not very necessary for us to impose a modulus, because a simple curved bracket will do. So I'm going to be replacing the modulus with a curved bracket because of the nature of the expression that I'm seeing here. As for this here, it is just going to be x plus 1 to the power of negative 1 over negative 1. And let's not forget about the plus c. So my final answer here is going to be a ln x squared plus 2x plus 1 minus minus become plus 3 over x plus 1 plus c. This is the result that I've gotten from part A, which we will be using in part B. So let me just rewrite it here first before I erase this, okay? So this result is ln x squared plus 2x plus 1, then plus 3 over x plus 1 plus c. And the next thing that we're going to do in part B is to do another integration. And this time, we are supposed to be integrating an expression, an integral that looks quite similar to this. Okay, so we are going to do this part B as a hence question, making use of the result that is from part A. So how are we going to be working on part B as a hence that is making use of our result in part A? So my suggestion is to try to see part B from another perspective. Okay, instead of just looking at part B as just simply a integration technique question, maybe we can try to look at part B as an area question. Because if I were to look at it as an area question, it is basically just trying to find the area that is bounded by the curve, and x is equal to 0 and x is equal to 2. And if I were to press this into my graphing calculator, that means sketching the graph of y is equal to modulus of 2x minus 1 over x squared plus 2x plus 1, my graph will look something like this. So if this is the x-axis, this is the y-axis, we'll have a graph that is like this, and it will go up this way here. This point here from my graphing calculator is 0.5, and here we have a 0. So what the question wants is to find the area that is between 0 all the way until 2. So here is 2, which means that we are supposed to find this area. Okay, because this area will represent what we are supposed to be integrating in part B. But with a modulus, we cannot do the actual integration. But what we can do is to try to break up this area into two parts. And how are we going to decide which are the two parts to break it up into? I'm going to remove the modulus, which means that if I were to replace the modulus with a plus or minus instead, we can actually draw two more graphs. One will be y is minus 2x minus 1 over x squared plus 2x plus 1. And the other one will be removing this modulus, replacing it by plus or minus with a minus. So the other one is going to be plus 2x minus 1 over x squared plus 2x plus 1. Let us take a look at the two graphs, one for this, the other one for this. If I were to look at this particular graph here, you will realize that this graph looks like this. Okay, where this is 0.5. I think I'm going to try to make use of half. Okay, half feels more like my kind of thing than decimal. Okay, so I'm going to just change this 0.5 into half. And here is actually also a half. So if you were to look at this and compare to this, you realize that this region here from 0 to half is actually this region here, which means when I try to do what the question is asking me for, which is to be integrating from 0 to 2 of this modulus of 2x minus 1 over x squared plus 2x plus 1, which now I am seeing it from the perspective of area instead of just simply integration technique. This region here can also be simulated by doing an integration from 0 to half of this, which is negative 2x minus 1 over x squared plus 2x plus 1. And now without the negative, in fact, we can even factorize out the negative. This will leave me with a 0 to half of 2x minus 1 over x squared plus 2x plus 1. And the integral of this, the indefinite integral version of this, we have already found it in part A. So we can actually make use of this result. As for this region here, let's see whether we are going to be getting it as something that we are going to see again in this. Okay, so if you were to draw this particular graph, this graph with the x-axis here and the y-axis here, and I've forgotten to name my x and y-axis, so let me just do that now. So this graph will be something like this. Okay, on your graphing calculator, here will be 0, the origin, and here will be half. And if you were to just compare this and this, you realize that this region here can be simulated by half to 2 of this region that is bounded by the curve and the x-axis. Okay, and of course the two vertical lines, x is equal to half and x is equal to 2. That is why for this region, we can also simulate it by integrating from half to 2 of this graph instead. 2x minus 1 over x squared plus 2x plus 1. And now what we have done is to successfully remove the modulus from the integral, giving us two other integrals which we can now make use of our result in part A to try to resolve them as definite integrals. So this is going to be negative. Let's put a square bracket. I'm going to bring in the result from part A, which is this over here. So it's going to be ln of x squared plus 2x plus 1 from 0 to half, plus this is just going to be ln of, again, x squared plus 2x plus 1. Oops, I've forgotten about this, so I do need to add that in. So let me just redo this part again. Okay, so it is going to be this plus 3 over x plus 1. So it's going to be from 0 to half, then plus. We definitely don't want this c to be appearing here. Okay, this is a definite integral. So it's going to be this. Once again, it is going to be this expression here, which is ln x squared plus 2x plus 1, then plus 3 over x plus 1. And this time, it is going to be from half all the way until 2. The next thing to do is pretty simple. I'm going to substitute the numbers in. For this, we are going to be getting a ln 9 over 4 plus 2. Then minus away, substituting 0 in, we're going to be getting a 3. Then plus, substituting 2 in, we are going to be getting a ln 9 plus 1. Substituting half in, we are going to be getting a minus ln 9 over 4 plus 2. And if you were to continue to simplify this, you will eventually get a number that is 2 ln 4 over 3. So this is for question number 8. Let's move on. Let's take a look at question number 9. Okay, let's take a look at question number 9. It is an APGP question. Question number 9A, we are given that for this arithmetic series, the first term is A and the common difference is D. And we are going to be comparing terms of this arithmetic series to terms of a geometric series. Let me just sketch out for myself a little table for me to just reorganize the information that is given to us by this question. Okay, so we are going to be comparing the arithmetic progression to the geometric progression, and according to what the question says, the first, third, and the 15th term are the same as the first, second, and the third term of the geometric series. Okay, so the first, the third, and the 15th term of the AP, they are going to be synchronizing to the first, second, and the third term of the geometric progression, the geometric series. So the first term of this is A, which means since they are the same, so the first term of the GP is also going to be equal to A. Then for the third term of the AP, it is going to be A plus 3 minus 1 times D. 15th term is going to be A plus 15 minus 1 times D. As for the geometric progression, if the common ratio is R, that means the next term is going to be A times R. The next term will be A times R, AR square. We are supposed to find D in terms of A. And what I think I'm going to try do is, if I will be taking this divided by this, okay, A plus 14 over D divided by A plus 2D. This, because they are also consecutive term of the geometric progression, so this will actually be giving me the common ratio, which is going to be exactly the same when I take this A plus 2D, which is the second term of the GP, divided by the first term of the GP, A. And I'm going to make use of this here, okay, less the R. This here to try to find D in terms of A. So for this that is here, let's cross multiply this. So it will be A plus 14D is going to be this times this, A plus 2D square. Multiplying this in, we have A square plus 14AD is going to be equal to, expanding this, we have A square plus 4AD plus 4D square. So A square and A square can be cancelled. I am going to bring everything over to the left-hand side. So on the left-hand side, sorry, I'm going to bring everything over to the right-hand side. So we will have a 4D square. Then this bring it over to the right-hand side. I'm going to have a 4AD minus 14AD minus 10AD. This is equal to 0. If I were to factorize out 2D, then we will be getting a 2D minus 5A. This is equal to 0. We are told that D is not equal to 0, obviously, because if D were to be equal to 0 for an arithmetic progression, every term will just be A. I don't even see the AP at all. So D is not equal to 0, which means that 2D minus 5A has to be equal to 0. This tells me that D is going to be equal to 5 over 2A. This is for part A. Let's check out part B next. So for part B, we are given a geometric series with the first term as sine theta and a common ratio as negative cosine theta. I want to show that in part 1, the sum to infinity is going to be an expression that looks like tangent k theta. And let's not forget that k is a constant that we do want to make sure that we highlight in our final answer in order for us to reply to what the question is asking for also, which is, k is a constant to be found. So we want to find this sum to infinity, and we are talking about a geometric series, which means that for the sum to infinity, the formula is A over 1 minus R. A is the first term. The first term that is given to us is sine theta for this geometric series, divided by 1 minus the common ratio, which is given to us as minus cosine theta. So we have a sine theta over 1 plus cosine theta over here. This can already be an answer, but the question requires us to change this a bit more into a form that is like tangent k theta. So let's try to manipulate this a little bit by using some trigonometric identities. I'm going to try to change the numerator to 2 sine theta over 2 cosine theta over 2. As for the denominator, we are going to make use of the double angle formula for cosine, And what we have is a cosine 2a is equal to 1 minus 2 cosine square a, which means that 2 cosine square a is going to be 1 plus cosine 2a. So I'm going to apply that to the denominator over here. So doing that, the denominator will become a 2 cosine square, replacing a by theta over 2. So we have a cosine square theta over 2. So this and this can be cancelled, this and this can be cancelled. We have basically just a sine theta over 2 divided by cosine theta over 2, and this is tangent theta over 2, or of course we can see this as a tangent half theta. So what is k? Therefore k is going to be equal to half, and we have shown what the question requires us to show. And in part 2, let me just write it down here. In part 2, we are now given that theta is equal to pi over 3. If theta is equal to pi over 3, we can actually find the numerical value for the first term. So let me write it down. The first term of this geometric progression, which is going to be sine theta, is going to be sine pi over 3. This is square root of 3 over 2. We can also come out with the, okay, not exactly us coming out with the common ratio, but we can calculate now the numerical value for the common ratio. Given theta, common ratio was given to us by the question as negative cosine theta. So this will be negative cosine pi over 3, which is negative half. So the sum of the first 7 terms again making use of the sum of GP formula, it is going to be the first term, square root of 3 over 2, 1 minus the common ratio to the power of the number of terms, which is 7, divided by 1 minus away the common ratio. So this is going to be square root of 3 over 2. This, if I have to press it into the calculator, we will have 129 over 128. This is going to be over 1 plus half. This is going to be 3 over 2. And simplifying this, we're going to be getting a 43 over 128 square root of 3. This is for question number 9. We are going to move on. Okay, now let's take a look at question number 10. We are given this curve C with the equation that is given to us. In part A, it is further given to us that for this curve C, it has no stationary point. So first, let us try to find dy dx. Y is given to us as ax plus b plus a plus 2b, which is a constant, divided by x minus 1. And just to prepare this for differentiation, what I think I'm going to do is to, okay, this is a constant. I'm going to try to bring the denominator to the numerator by rewriting it as this. Okay, I personally find it a little bit easier for me to do my differentiation. So dy dx is going to be equal to, differentiating this is a, differentiating b, which is a constant, is 0, plus a plus 2b. Differentiating this is going to be a minus 1, x minus 1 to the power minus 2, chain rule, differentiating this is going to be equal to 1. So we have a minus a plus 2b over x minus 1 square. So this is dy dx. To work on stationary point, we are going to make dy dx 0. So I'm going to let dy dx be equal to 0, which means that it is going to be this a minus a plus 2b over x minus 1 square is to be equal to 0. So a plus 2b over x minus 1 square is going to be equal to a, which means that x minus 1 square is going to be equal to a plus 2b over a. And if I were to continue from here, we can actually write it in this form. This will be square root both sides, right? So it'll be plus or minus square root of a plus 2b over a. In fact, this is where we can already pause and just think about the fact that dy dx is not solvable. Okay, I said like dy dx is equal to 0 is an equation that is not solvable because according to what the question says, there is no stationary point. So in order for this to be not solvable, that means we will not be able to get a real value for x as the solution, we can really see the hint from this expression that is within the square root. In order for x to have no solution, I mean, if I were to just do one more line, it is going to be 1 plus or minus square root of a plus 2b over a. We will just simply let this a plus 2b over a to be strictly less than 0 in order for x to have no solution. Okay, in order for this equation here to have no solution. So we'll let this expression that is within the square root to be less than 0, multiplying a across to the other side without having to change the inequality sign, because the question here is telling me that a is bigger than 0. So multiplying this across is just going to be a plus 2b. Inequality sign remains exactly the same. In fact, I'm going to just be giving this as the relationship between a and b to answer part A of this question. Next, it is now given to us that b is equal to minus 2a. We are supposed to sketch the graph of c. So if b is minus 2a, let me just rewrite what that is given to me here first, okay? Using, for part B. So y is given to us as ax plus b plus a plus 2b over x minus 1, right? So according to the question, b is going to be equal to minus 2a. So I'm going to replace all the b's by minus 2a. So plus a plus 2, this is minus 2a over x minus 1. And this is going to be equal to ax minus 2a minus 3a over x minus 1. We are supposed to sketch the graph. Based on this that we have here, we know that the graph that we are going to be sketching will have two asymptotes. One will be the oblique asymptote. The other one is going to be the vertical asymptote. Let us draw the asymptotes first. So my graph will be something like this. Okay, this is going to be the y-axis. And let me draw my x-axis as here. Okay, we should always try to draw in the asymptotes first, because asymptotes are reference lines. Reference lines should always be drawn before I draw the actual thing. That is why they are called the reference line. Okay, so we are going to be drawing out the reference line, then drawing the solid part of the graph, the actual graph based on the reference line. So x is equal to 1 is the vertical asymptote. We have it here. Okay, so I'm going to name this x is equal to 1. The oblique asymptote is y is equal to ax minus 2a. According to the question, a is a bigger than 0 number. So this oblique asymptote will have a positive gradient. And if I were to let me just write it down in red color. So my oblique asymptote is y is equal to ax minus 2a, okay? Which means that for this oblique asymptote, which is going to be a linear line with a positive gradient, this point here is going to be at 0 minus 2a. As for this point here, it is by letting y be equal to 0. So I'll let ax minus 2a be equal to 0. We will be getting x to be equal to 2. And the reason why I need this, okay, this point here to be 2, 0, is not because we are actually going to be getting marks for indicating the details of the oblique asymptote, okay, because these are reference lines. We need to label them, but we don't actually need to give the specific features of them. I think it is optional, but we do need to draw a proper reference, because as I try to sketch in this line, right, I want to make sure whether this line, which has a positive gradient, is before, at, or after the point where it cuts the x-axis. So now with this verification, where we see that the x-intercept is 2, 0, this is when x is equal to 1. We know that the oblique asymptote is going to be cutting the x-axis to the right of 1. So we have our graph with an oblique asymptote that is something like this. I am going to name this as y is equal to ax minus 2a. So we are going to just let a be a positive number, let's say 1. I'll press it into the calculator to give myself an idea of how this graph is going to look like. Or another strategy is based on the relationship that you have found in part A. If you have to sub A, if if you set b to be equal to minus 2a, you realize that it actually satisfies the relationship that is mentioned in part A. So you will also be able to deduce that for the graph that we're going to be drawing, it will have no stationary points. But anyway, I think the fastest way is to just let a be equal to, let's say, 1, press it into the graphing calculator, take a quick look at the shape of the graph, and you'll realize that it looks something like this. Let me just sketch it. So it will be like this. Okay, and the other part of the graph will be like this. There's some details that we want to discuss about, but let me just finish drawing the graph first. The detail will be this part here, because we want to try to check also whether this is going to be above the x-axis or whether it is going to be cutting below the x-axis. I mean, I'm drawing there because I already know it is going to be above the x-axis. How do we decide that it is going to be above the x-axis? One of the quickest way is to just simply let x be equal to 0. Okay, if you were to let x be equal to 0, you're going to get y to be equal to a. And a is a positive number. That is why I know it is cutting at the place where it is above the x-axis. And this point here is 0, a. We will also be required to indicate the coordinates of this point and this point. And this will require us to let y be equal to 0. So if I were to let y be equal to 0 for this entire expression here, so ax minus 2a minus 3a over x minus 1, if I were to let this be equal to 0, all the a's can be cancelled. We have a x minus 2 minus 3 over x minus 1 is equal to 0. If you were to solve this equation, you're going to get two values of x. So 1, 2, and these two values of x will be the x-intercept that we have here. So one of them is going to be negative 0.303. Okay, so the x-intercept of this will be negative 0.3030, and the other value of x that you'll be finding will be 3.30. Okay, so we have another x-intercept, and this will be the graph of y is equal to ax minus 2a minus 3a over x minus 1 that is required from part B. And the next thing that we want to do, according to what the question says in part C, is to sketch the graph of y is equal to ax minus a. Let me just very quickly write it down here for myself to reference. So for part C, we are sketching a y is equal to ax minus a. One thing that we should be able to observe is that for the oblique asymptote, y is equal to ax minus 2a, it shares the same gradient as this line, which means that this line that we are supposed to be sketching on here is going to be parallel to the oblique asymptote. We will also need to find out whether this line is going to be above or below this oblique asymptote. That is pretty easy. If I were to let y be equal to 0, we have this to be equal to 0. Then if y is equal to 0, when y is equal to 0, that means x here is going to be equal to, when y is equal to 0, sorry, we should be letting x be equal to 0. I want to find, my aim is to try to find the x-intercept. So when x is equal to 0, when x is equal to 0, y is equal to minus a. So we know that this line here, the y-intercept, is going to be equal to 0 minus a. And this point here, according to what we discussed just now, this point here is a 0 minus 2a, which means that 0 minus a, okay, from here, 0 minus a is going to be above here. Okay, so we do know this point already. And the one that I've erased just now, which I now realize I do need it, is to let y be equal to 0, because I want to try to find out also how it is going to be cutting the x-axis. So if I were to let y be equal to 0, which means that we will have x minus a to be equal to 0, x is equal to 1, which is actually this point over here. So my graph is going to be parallel to the original oblique asymptote, passing through a point that is cutting the y-axis above the place where the original oblique asymptote is cutting, and it is going to be passing through this point, x is equal to 1. So the line is going to be something like this here. and here. Okay, this will be the line y is equal to ax minus a. There is actually an intersection between these two. I'm going to mark out the intersection. It is here. In fact, it is pretty easy for us to find the coordinates of this intersection. Let me just find it because it is going to be useful for what we are going to be doing in part D anyway. So the coordinates of the intersection point will be, if I were to equate the expressions of the two graphs together. So we will just be letting this, which is the first graph, ax minus 2a minus 3a over x minus 1 be equal to this, ax minus a. The first thing that I'm going to do is to remove a, okay, because a happened on the left hand side, a happened on the right hand side. So all these a's can be cancelled, leaving me with x minus 2 minus 3 over x minus 1 is equal to x minus 1. So for this that I have here, we have x and x can be cancelled. If I were to bring this over to the other side, we have a minus 3 over x minus 1 is going to be equal to 1. So x minus 1 is going to be equal to minus 3x is going to be equal to minus 2. So with x is equal to minus 2, if I were to substitute this back into here, I know y is going to be equal to a times of minus 2 minus a. This is going to be minus 3a. So the coordinates of the intersection between these two will be minus 2 minus 3a, which is actually this point over here. So here is minus 2 and minus 3a. So with this information that I have, I think I am ready to try to find D, especially when the question in D says hence. So we are going to be making use of the previous result. So for part D, hence we are going to solve this inequality, x minus 2 minus 3 over x minus 1 is less than or equal to x minus 1. How are we going to be making use of the previous result? We must first find the similarity between this and the previous one, which if I can just rewrite for you, probably you can very easily see that similarity. This, if I were to just look at what I have here, which is this graph that I've just drawn, it is actually just a being 1, right? So it will be like 1x minus 2 times of 1 minus 3 times of 1 over x minus 1 is less than or equal to this. I'm going to reference it to this. And if I were to also let a be equal to 1, we in fact have 1 times x minus 1. So for this case that is here, it is like looking at this graph, except that all the a's are going to be equal to 1. That is why this is a hence question. And in order for us to solve this inequality, it is when this curve is lower than this curve. And if you were to look at that graph, when will the black color graph, okay, which is this curve, be at the bottom of the red color graph, which is this? So that is happening here, right? The black color graph is below the red color graph. The red color graph is ax minus a. When a is equal to 1, it is x minus 1. So, I mean, a can be equal to 1, right? Because the question did mention to us that a is a positive number. So anyway, it is going to be this portion of the graph. And there's one more portion where the black color graph is below the red color graph. And that is going to be this portion here. Okay, it is when the black color graph is below the red color graph. So based on the graphs that we have just drawn, we can see that my answer to this inequality is when x is less than or equal to 2 or when x is strictly bigger than 1. So this is for question number 10. Next, we are going to look at a vectors question, question number 11. First, we are looking at a pipeline, which is a straight line. It is going to be passing through 2 points P and Q. So for point P, the coordinates that is given to us is, for point P, it is 1, 1, 3, 6, 92, and an unknown P as the Z coordinates. As for point Q, we have this as a 200, 20, and negative 15. And according to what the question says, point P must be lying below point Q. Okay, that's what the question says. Level of P is below that of Q, which means below, high, low, high, low. And that is with reference to the z coordinate, right? So the z coordinate for Q is -15. If the coordinates, if point P is supposed to be below point Q, that means P must be a number that is even less than -15. And we are supposed to solve for the value of P. So the hint that is given to us that will allow us to solve for P is that this distance here is 939, okay? So this distance is the modulus of PQ. That is why the first thing that I'm going to do is to find vectors PQ. For this vector PQ, it is going to be OQ minus away OP. OQ is going to be 220 minus 15 minus OP 1136, 92, and P. This is going to be equal to -936, -72, -15 minus P. This is PQ, vector PQ, and the distance, which is modulus of PQ, is given to us as 939. So the distance based on the position vector of PQ, this is going to be square root of -936 square plus -72 square, then plus -15 minus P square. This is equal to 939. We're going to square both sides, and we're also going to expand what we have within here. And expanding what we have within here is giving us 81280 plus 225 plus 30P plus P square. This is equal to, squaring this, 881721. Bring everything over to the left hand side. It is going to be a P square plus 30P minus 216 is equal to 0. Factorizing or just simply solving this using a calculator, you're going to get P to be equal to -36 or P to be equal to 6. And when P is equal to 6, we are rejecting. Why is that so? Because according to what we have interpreted from the question, P must be a level that must be at a level that is below Q. That is why this P must be a number that is less than -15. So we are choosing this, a number that is less than -15. Let's look at the next part of this question, part B. For part B of the question, we are looking at a plane which is going to be that is simulating this rock surface, that is this rock layer that is under the ground. So this plane is going to be passing through 3 points. So let me just do a quick sketch of this plane, okay? So let's say the plane is this. It is going to be passing through 3 points. Let's say they are these 3 points. One of the points has coordinates of this 400, 600, -20. Another point, let's say this is, let's say 500, 200, -70, and one more point, for example, this one here, 600, -340, and -50. So we have a plane that contains 3 points where the coordinates are given to us. So in part B, we are supposed to find the Cartesian equation of this plane. So the first thing that we want to do is to find a vector that is perpendicular to this plane. We want to find the normal to this plane. So let me try to find these 2 vectors, because these 2 vectors which connects points that are on the plane will be giving us vectors that are parallel to the plane. Crossing them will give us the normal vector. So let's find this first, which is going to be 500, 200, -70, minus 400, 600, -20. What is this giving us? This is giving us a vector that is parallel to the plane. So this is -50 minus 281. So this is parallel to the plane, which means that -281 is also going to be parallel to the plane, which I'm going to be using later since it's a number that is more friendly for my calculation. Let's find another vector that is also parallel to this rock layer. And that is this vector over here, which is going to be 600, negative 340, negative 50, minus away 400, 600, negative 20, which will be giving us a 10 of 20, negative 94, and negative 3. So we're going to be using this instead of the entire thing as the vector that is parallel to the plane. So the normal to the plane, normal vector to the plane, or normal to plane. We have possible normal to the plane. We'll be doing cross product of the two vectors that we have found that are parallel to the plane. So I'm going to take negative 2, 8, 1 cross 20, negative 94, and negative 3. Crossing this will give us a result that is 70, 14, 28, which we can also re-express by factorizing out 14, leaving me with 5, 1, 2. So this is normal to the plane. This 5, 1, 2 will also be normal to the plane. And now we can find the dot product equation of the plane. So equation of the rock surface, or equation of this plane that represent the rock surface, will be r dot the normal vector. I can either use this, or I'll probably just use the more friendly number, the smaller number. It's going to be equal to the position vector of a point that is on the plane. I can choose any points. Let's just choose this point here, which is going to be 400, 600, negative 20, dot the normal that I've chosen. And if you were to evaluate this dot, I will get a 2, 5, 6, 0. And the question requires us to give the Cartesian equation. So replacing r by x, y, z, x times 5, 5x, y times 1, it will be y, plus 2z. This is equal to 2, 5, 6, 0. This is the Cartesian equation of the plane. Let's move on to part C. For part C, we are looking at the intersection between the straight line part of the pipe and the rock layer. Okay, we are trying to find the coordinates of the intersection, or the point where the pipe meets the rock. So the situation is something that is like this. Okay, it is this pipe that passes through the point PQ. Okay, and the rock surface. So let me just write it as rock. And this is the pipe line. For the rock, we actually found the equation. The dot product equation of the plane that represent the rock layer is r dot this is equal to 2, 5, 6, 0. We actually don't have the equation of the line that is representing the pipeline. So we have to find that line with P that we have found. This P that the P that I meant is this P, okay? We found P to be equal to negative 36, which means that PQ, okay, PQ will represent a vector that is parallel to the pipe, is going to be equal to negative 936, negative 72, using the result that we have in part A, okay? Negative 15 minus P is negative 36. So I'm going to be replacing it by negative 36. This is equal to negative 936, negative 72, and 21. So this is going to be the vector that is parallel to the pipeline P that passes through PQ, which means that the equation of the pipeline, equation of this pipeline will be R is equal to, it passes through the point P and Q, so I can use the coordinates of either of them. Let me just make use of the coordinates of point Q, which will be translated into a position vector as 220, negative 15, plus lambda of a direction that is parallel to this pipeline is this. So this is the equation of the pipeline. This is the equation of the rock. At the place where they intersect, at the place where they meet, they happen simultaneously. Okay, the point happens simultaneously between the two equations. So we're going to try to solve this as a pair of simultaneous equation. Simultaneous equation as this is like the first equation, this is like the second equation. What that is synchronizing is this R. So I'm going to just solve this as a pair of simultaneous equation where R happens simultaneously at this particular point. So I'm going to substitute this into here. So this is going to be a 200 minus 936 lambda, 20 minus 72 lambda, minus 15 plus 21 lambda. So this, substituting into here, 512 is equal to 2560. Evaluating the dot product will be 5 of 200 minus 936 lambda plus 1 time of 20 minus 72 lambda plus 2 times of negative 15 plus 21 lambda. This is equal to 2560. If you were to solve for lambda, it is going to be equal to negative 1/3. So this is the value of lambda when this happened. So I'm going to substitute this lambda back into here to find the position vector of that point. So the position vector where pipe line meets the rock. Okay, this is going to be equal to 200, 20, negative 15 plus lambda, which is negative 1/3 of negative 936, negative 72, 21. This gives us a 51244, negative 22, which is close to perfect. You know why? Because the question is not asking for the position vector. The question is asking for the coordinates of the point where it meets. So we do need to re-express our answer in the coordinate form, which is this, negative 22. Let's look at the last part, part D. So in part D, we are now going to try to find the angle that the pipe line between P and Q meets with the horizontal. Okay, the question described to us the horizontal, but we know that for the horizontal, what is so distinct about the horizontal? The normal is going to be vertical, right? So if I were to be looking at that pipeline that passes through the point P and Q, with reference to the horizontal, we are going to be referencing to a plane where the normal is 0, 0, 1. Okay, because the normal has to be vertical with respect to the horizontal plane. And as for the pipeline, we have found out that it is parallel to the vector negative 936, negative 72, and 21. What the question interested in is this angle over here. And in order for us to find this angle, I'm actually going to reference it to, with this as 90 degrees, I'm going to reference it to this angle instead. Because this angle is the angle that is between this and this. This allows me to bring in dot product. So for a 0, 0, 1, dot negative 936, negative 72, 21, it is equal to the modulus of 0, 0, 1, modulus of negative 36, negative 72, 21, cosine. We are writing down the dot product equation. Cosine of this angle. What is this angle? This angle is 90 degrees minus away theta, right? So cosine of 90 degrees minus theta. And treating the situation that we are looking at here as an acute angle for this, we are going to just do a bit of improvisation by imposing a modulus to this. But anyway, when you evaluate this, it is going to be positive. Okay, so it doesn't really matter whether there's a modulus or not. So it will be a cosine 90 degrees minus theta is going to be equal to a 21 over 939, which is the modulus of this multiplied by the modulus of this, which means that 90 degrees minus theta is going to be cosine inverse of 21 over 939. This makes theta 90 degrees minus cosine inverse of 21 over 939. This gives us the angle of 1.3 degrees. We have one more question, the last question, question number 12. Okay, now let's take a look at question number 12 over here. And in part A of question number 12, it is given to me before part A is being mentioned. Okay, we are supposed to be writing down a differential equation. So we are given that the rate of change of the population here, the rate of change of the population is proportional to the population. So what it is saying is the rate of change of the population, dp dt, is proportional, where k is the constants of proportionality, is proportional to the population itself. We are supposed to solve this when we are given some information that is quoted by the question. Here we are going to be making use of it in a short while. Okay, so let's just try to solve this differential equation first. We are looking at a first order variable separable kind of differential equation. So one thing that I'm going to try to do is to bring the p over to the dp dt side. So bring this over to the other side, we have a 1 over p dp dt. This is equal to k. Integrating both left and right hand side with respect to t. On the left hand side, we are going to be left with 1 over p dp. And k is a constant. I'm bringing it out of the integration notation. It is going to be integration of 1 dt. So this is going to be ln modulus of p. This is going to be kt plus an arbitrary constant, which I'm going to go for a to be that arbitrary constant. So modulus of p is going to be e to the power of kt plus a, which I can also rewrite this as e to the power of a, e to the power of kt, which means that p is going to be plus or minus e to the power of a, e to the power of kt, which I am going to rewrite this as just simply b, e to the power of kt, where b here represents plus or minus e to the power of a. And we're going to make use of the information that is given to us by the question here, this line here, okay, to try to solve for the two unknowns b and k. The first one is initially the population is observed to be 50. Initially tells us that t is equal to 0. So when t is equal to 0, the population is equal to 50. Let's substitute this in. So b e to the power of 0 is equal to 50. What is e to the power of 0? That is 1. So b times 1 is equal to 50 simply tells us that b is equal to 50, which means that for this equation here, we have a p is equal to 50 e to the power of kt. We need to solve for k, and we do have another piece of information that will allow us to solve for k, because the question says that when t is equal to 10 days, p is equal to 100. So let's substitute this in. It is going to be 50 e to the power of 10 times of k is equal to 100. So e to the power of 10k is going to be equal to 2. 10k is going to be equal to ln 2, which means that k is going to be equal to 1 over 10 ln 2. So we have p as 50 e to the power of k times t. So this times t, it is going to be equal to 1 over 10 t ln 2. This is for part A. Part B, we have a differential equation that is given to us, and we are supposed to solve that differential equation. Let me erase this first. Okay, so in part B, we are now given a refined model to the population growth of the insect. Let me write down this refined model. It is dp dt is given to us as lambda p 500 minus p. And we are also supposed to solve the differential equation of this refined model and trying to find an expression of p in terms of t. This is once again a variable separable, first order variable separable kind of differential equation. So I'm going to bring the entire p's expression, dividing across to the other side to let it join with dp dt. So dividing this across, we have a 1 over p 500 minus p dp dt is going to be equal to lambda. I'm going to integrate both the left and right hand side with respect to t. And on the left hand side, when I integrate this with respect to t, I'm going to be left with a 1 over p 500 minus p dp. And lambda is a constant. I'm going to take it out of the integration notation. So on the right hand side, when I integrate it with respect to t, it is integrating 1 with respect to t. To integrate this over here, we are going to apply partial fraction to manipulate the integral that is within so that it can be integrated. So applying partial fraction to this, we will be getting this to be re-expressed as 1 over 500p plus 1 over 500 minus p dp. This is equal to lambda of integration of 1 dt. Let's factorize out the 500. It just looks like not a very friendly number to stay within the integral. So I have a 1 over 500. So now I have a 1 over p, which is way nicer. So this is 1 over 500 minus p dp lambda integration of 1 dt. So 1 over 500, we have it here. This, when I integrate it, it is going to be ln of modulus of p. Integrating this is minus ln modulus of 500 minus p. This is lambda t plus c. Let's multiply 500 across, and for this, let's combine it into one single expression using the law of logarithmic. So this is going to be p over 500 minus p is equal to 500 lambda t plus 500 c. Let's inverse, okay, the logarithmic function, which will be giving us this 500 minus p is going to be e to the power of this, which I'm going to just quickly write this as e to the power of 500c e to the power of 500 lambda t. And removing the modulus, giving me a p over 500 minus p is plus or minus e to the power of 500c e to the power of 500 lambda t. And I'm going to just replace this, like how we have done it in part A, by an arbitrary constant. So I'm going to call this entire expression here as d e to the power of 500 lambda t. So this d here represents plus or minus e to the power of 500c. So for what we have here, let's try to solve for the unknowns, which are two of them. One is going to be d, the other one is going to be equal to lambda. So to solve this, once again, we're going to make use of the two pieces of information that is given in the first paragraph of the question. Initially, the population is observed to be equal to 50. So when t is equal to 0 initially, we know that p is equal to 50. So substituting it in, we have a 50 over 500 minus 50 is equal to d e to the power of 0. This gives us the value of d to be 1 over 9. The other piece of information, that is when t is equal to 10, p is equal to 100. So what we are looking at is now a 100 over 500 minus 100 is equal to d, which we have found it out that it is 1 over 9, e to the power of 500 lambda times t, which is 10. So we will now have this is e to the power of 5,000 lambda. Multiplying 9 across to the other side, this is equal to a 9 over 8. So 5,000 lambda is ln of 9 over 8. This tells us that the value of lambda is going to be 1 over 5,000, then ln of 9 over 8. So we can now write down p as I write down this equation as this is equal to d, which is 1 over 9, e to the power of 500 lambda, which is this 1 over 5,000 ln 9 over 8. So we have a p over 500 minus p is 1 over 9. then this is going to be equal to e to the power of 1 over 10 t. Oops, I've missed out a t. So it is going to be 500 lambda t. So I still need to multiply this whole thing here, okay, by t. So this is 1 over 10 t, then I have a ln of 9 over 8. We still need to make p the subject. So let me divide this across to the other side, which is p over 1 over 9 e to the power of 1 over 10 t ln 9 over 8 is equal to 500 minus p. I just need a little bit more space in order for me to find p in terms of t. So let me erase this and continue here, okay? So for what I have so far, which is this, let me bring the denominator up. Okay, so p divided by this is going to be equal to 9. Then p e to the power of, bringing this up, it is going to be e to the power of negative 1 over 10 t ln 9 over 8 is equal to 500 minus p. I'm going to bring all the p's over to one side. So this one over to the left hand side. This will be 9p e to the power of minus 1 over 10t ln 9 over 8 plus p. This is equal to 500, factorizing out p and dividing the non-p part over to the other side. It is going to be 500 over 9e to the power of minus 1 over 10 t ln 9 over 8 plus 1. Goodness me, it is such a long process for us to get p. How many marks are we going to be awarded? 6 marks. I think it is quite fair. It is not too bad. Let's look at the last part of this question. In the last part of this question, we are supposed to try to make use of this refined model and try to guess what is the population of the insect in the long run. So for long run, we are going to interpret it from the math perspective as when t goes to infinity. This is the refined model. So for part C, long run, when t goes to infinity, that means p will become 500 over this. Okay, this is e to the power of a negative number. In fact, when t goes to infinity, it is going to be e to the power of a super negative number, which will make this to become a 0, right? Okay, in case that is a bit harder for you to observe, we can definitely rewrite this expression here as 9 over e to the power of 1 over 10 ln 9 over 8 multiplied by t. So when t goes to infinity, this expression, which is 9 over a super big value, will go to 0. This entire expression will go to 0. So this will become a 0 plus 1, which is equal to 500. So based on the refined model, the population of the insect will become 500. And according to what the question is asking us, comment on, just based on this value that we have found, right? Comment on why this refined model is an improvement from the first model. What did we get in the first model? Let me just write down to help us to recall a little bit, okay, what we have gotten in the first model. So this is the refined model. For the first model, we got a p is equal to 50 e to the power of 1 over 10 t ln 2. So if I were to just compare this to the previous model, okay, because that is what the question asks us to do, compare the population when it is in the long run. So when t tends to infinity, based on the previous model, based on A, P will become, okay, this is T. Okay, so we have a e to the power of, when this goes to infinity, the whole thing will go to infinity, right? So if the whole thing goes to infinity, P will also go to positive infinity. So comparing this result with the refined model, this is definitely an improvement because according to the refined model, the population of the insect will stagnate to 500. But according to the original, the very first model, the population of the insect will just go on and on and on. It will just go to positive infinity, which is not very realistic. That is why, based on this, I would say that the refined model is an improvement.